Welcome to the course on computer design of electrical machines. So we'll have a lecture 5 today on transformer design part 2. We'll have a outline of today presentation starting from transformer design, which we are continuing from last lecture about the yoke design and window design. Then we'll go to design of windings and thermal and mechanical performances and transient behavior, some of the phenomena of transient, which are very important in case of the transformer. And then of course exercise and numerical problems and references like. So coming to the again to continue as a transformer design. So we come to the now design of yoke. So the yoke of the transformer connect the legs and provide the least reluctance path. The yoke portion does not have windings, and so the iron loss or core loss in the yoke can be minimized by increasing the yoke area, thereby reducing the operating plug density. And generally, yoke area is made 20% more than the lag area. This yoke sections can be rectangular or cruciform. Well, this is the, you can see the typically the structure of the single phase transformers of cell type, core type, and the upper portion we call it the yoke, and the winding on which winding is really wrapped, that called the limb, or we also call core. And you can just see how it is in case of the transformer, the upper portion called this yoke. And the following these figures show the various form of yoke for cruciform and rectangular core legs as well as limb, and cruciform leg can also have a rectangular yoke shape, as you can see in typically different figures like here. Now coming to for its design, as given a dimension here, the height of core is given hy and the depth is given like dy. So for a rectangular yoke, the depth dy of the yoke will be the same as the depth of the core, and this will be equal to the width of the largest core stamping A, and the height of the yoke hy can be in general be taken as 1 to 1.5 times the width of the leg, and area of the yoke, that is ay equal to dy into hy, that is equal to 1.15 to 1.2 times the AGI for hot roll, and normally AY equal to AGI for cold roll, grain rotated steel, which you are using for assembling this yoke as well as core with the laminations like of this material. So now coming to typically design of window, the area of the window can be determined from the output equation of the transformer, and area of the window is AW equal to Q in kVA divided by 2.22 or 3.33 or 6.66 F delta Bm AI AI into Kw to 10 power minus 3. If W is the width of the window and HW is the height of the window, then the limb to limit the leakage reactance of the transformer HW is made more than AW. So in practice, the ratio AW and WW lie between 2.5 to 3.5, which really you can say control the leakage reactance, and or you can modify the value of leakage reactance, which affect the performance, typically the voltage regulation of the transformer as well as short circuit current in case of the power transformer. Now coming to case of your single phase core type of transformer, after designing the core, yoke sections and window sections, the overall dimensions could be completed. The figure shows overall dimensions of the single phase core type of transformer, where H is the typically overall height, W is the overall width, D is the distance between the adjacent limb, and small d is the diameter of subscribing circle, and WW is width of the window, HW is the height of the window, HY the height of the yoke, and dy the depth of the yoke, as you can see in the figure all the dimensions. So you can call it from this figure, the dimension are given here. Overall height will be equal to H equal to HW, height of the window plus 2HY, that is both side of the yoke height, bottom as well as top, and distance between the adjacent limb, that D will be WW plus A, and overall width W will be D plus A, and the depth of the yoke will be equal to dy equal to A. Now in case of the three-phase transformer, typically the yoke overall dimensions will be, the dimension will be by overall height will be HW equal to HW plus 2HY, similar to like a single phase transformer, and the distance between the adjacent limb will be D equal to WA plus A, and overall width will be W equal to 2D plus A. Now in case of single phase cell type of transformer, as you see in the figure, the typically you can call it the gross core section of the central limb is equal to 2a into b, and overall width w equal to 2w plus 4a, and overall height h equal to hw plus 2hy, that is equal to hy plus 2a. So note here is the ratio b upon 2a is equal to 2.5 in general we take it. Now coming to dimensions of three-phase cell type of transformer. So dimensions are given as the gross core section area of the central limb is 2 into b, and overall window is w equal to 2w plus 4a, and overall height is equal to 3hw plus 4hy equal to 3hy plus 4a, as you can see in the typically dimension here. So now coming to like typically window space factor. So window space factor, it is the ratio of the copper area in the window to the overall window area, and normally it is related to typically the voltage winding rating of the voltage rating of the winding of highest rated voltage. So kW equal to 8 upon 30 plus kW for the rating about 20 kVA, and kW equal to 10 upon 30 plus kV for transformer rating for 52,200 kVA, and kW equal to 12 upon 30 plus kV for rated above 1000 kVA. And why it is related to the highest voltage rating of kV? The reason being obvious that the insulation requirement increases with the voltage rating, highest rating voltage or HV winding voltage rating. So now the area of the window depends upon the total conductor area and the window space factor. So area of the window AW equal to total conductor area divided by window space factor. So that's in 2 into AW TP divided by KW for single phase transformer, and that is equal to 4 APTP divided by KW for three phase transformer. So where AW is the height of window into width of the window, that is equal to H into HW equal to WW, and the ratio of height to width window will be HW divided by WW is between 2 to 4. So now coming to the design of windings, you can see how the transformer winding looks like on this three-phase transformer, and here we see that we have a rectangular layer type winding, and all that you can say parts are written related to the winding like tap lead, tap changer, high voltage, low voltage bus, low voltage pushing connection, flexible bus, phase, coil, high voltage lead, core ground, tunable, and step core, then the side braces and support type, then bottom support and inner base barter insulation. So now you can see for different type of the winding, for core type of single phase and three phase, how winding are put on the two limbs and three limbs of three phase transformer, and in cell type transformer of single phase and three phase cell type transformer, how winding are placed. That's about typically like animated concept, but you can see physical winding on the right side, how with the paper insulation is put on the winding and how winding is put, as a couple of people are putting this winding on the typically on the transformer core. And you can just see how the transformer winding is really put on big transformer with the proper insulation. As you can see, here's the winding, and then the continuously transparent cable and rectangular wire. Then you can see aluminum strip winding, how it is there. So after looking this winding, so we can say the design of winding, the applied volt for finding the turns as well as the cross section area. For that purpose, we say the applied voltage V1 is approximately equal to the voltage induced. So V1 equal to E1 equal to 4.44 pi m FT1, that is ET into T1. The number of primary turns or turns per phase, that is T1 equal to V1 upon ET in case of single phase transformer, and equal to V1 per phase upon ET in case of three phase transformer. And the second is number of secondary turns or turns per phase. So T2 equal to V2 upon ET in case of single phase transformer, and T2 equal to V2 per phase upon ET in case of three phase transformer. Now coming to find out the primary winding currents or current per phase. So I1 is kVA into 10 power 3 by V1 for case of single phase transformer, and equal to kVA into 10 power 3 into 3 V1 per phase in case of three phase transformer. And the step 4, to find out the cross section area of the primary winding conductor, that is A1 equal to I1 upon sigma millimeter, where the sigma is your current density in ampere per millimeter square. Similarly, we can find out secondary winding currents, I2 equal to kVA into 10 power 3 divided by V2 in case of single phase transformer, and equal to kVA into 10 power 3 into V2 phase in case of three phase transformer. And the step 6 is cross section area of secondary winding conductor, that is A2 equal to I2 upon sigma in millimeter square. Now knowing the number of turns and cross-section area of the primary and secondary winding conductors. So number of turns per layer in the winding height of HW and number of layers in the window width of W can be found out. And you have here now the type and choice of the windings. So there are different type of winding like cylindrical, helical, continuous disc and layer in case of transformer. So you can just see the different types of winding, namely cylindrical, helical, layer and continuous disc winding are generally used depending upon the voltage and current rating. And cylindrical winding, it may use circular, rectangular or strip conductor. It is generally wound with many layers. And the LV winding, rectangular conductor up to 6.6 kV and 600 to 750 kVA, current between 10 to 600 ampere. Now you can just see how the cylindrical winding looks like, and starting as a from different part of the figures starting end to ending end with the conductors as well as the insulation in between the cylindrical winding. So now coming to second kind of winding like helical winding. Helical windings are also referred as a screw or a spiral winding, with the each term accurately characterize the coil construction. And a helical winding consists of a 3 to more than 100 insulated strands wound in a parallel continuously along with the length of the cylinder and with the spacers inserted between adjacent turns or discs, and suitable transposition included to minimize circulating current between the parallel strands, as you can see in the diagram. So you can see how the helical windings of helical winding, then your double helical winding, how it goes, and how it is your disc helical winding really put into practice. Like now, defining all three with the a single helical winding consists of winding in an axial direction along a screw line with an inclination, and there is only one layer of the turns in each winding. And B, the advantage of the double helical winding is that it reduces eddy current loss in conductor, and this is on account of the reduced number of parallel conductors situated in the radial direction. And see, the in disc helical winding, the parallel connected strips are placed side by side in a radial direction to occupy the total radial depth of the winding. Now you can just see how it is multi-layer helical windings are commonly used for high voltage rating of 110 kilovolt and above, and these types of winding consist of several cylindrical layers concentrically wound and connected in series, and the outer layers are shorter than inner layers. And to distribute capacitance uniformly, these windings primarily improve the surge behavior of the transformer, as you can see in the diagram of the winding of multi-layer helical windings are there. So another kind of winding, a disc winding, can involve a single strand or several strands of insulated conductor wound in a series or parallel disc of the horizontal orientation, with the disc connected at either the inside or outside of a crossover point, as you can see here, like how it's. So each disc comprises multiple turns wound on over the other turns, with the crossover alternating between the inside outside. And most winding of 25 kilovolt class and above used in core form transformer and are disc type. And given the high voltage involved in the test and operation, particularly attention is required to avoid high stresses between disc and turns near the end of the winding when subjected to tangent voltage surges. And you can just see how disc winding with the inner outer core winding is placed there, and how crossover the windings turns there, as you can see the clear animation of winding placing of this type of winding. So now coming to crossover windings are used for high voltage windings of the small transformer, and the conductors are paper covered round the wires or the strip, as you can see in the diagram. So the windings are divided into number of coils in order to reduce the voltage between the adjacent layer, and these coils are axially separated by distance of 0.5 to 1 millimeter, and the voltage between adjacent coils will not be more than 100 to 1000 volt to meet the insulation requirement. Like so now coming to the layer winding consists of several cylindrical layers wound concentrically and are connected in series as shown in the figure below. As you can see, layer like a single layer and two strands wound parallel on this transformer. So layer windings are used for windings rated above 100 kilovolt, with the number of layers dependent on the voltage rating, and generally the outer layers are made shorter to distribute the winding capacitance uniformly, and several layers can be wound on top of one another, with the layers separated by solid insulation ducts or combination, and several strands can be wound in parallel if the current magnitude so dictate, means if current is higher in the winding. So now you can see how the taping is put on the out of winding and how the paper insulation is provided for coming out of the winding and how the copper foil conductors are placed there. Of course, we use the foil in some of the transformers for reducing the eddy current losses in the conductor. So this is typically, you can say, how circular layer type of windings are placed on the transformer, how it is really wound and how finally finished windings transformers coils are shown here. So now coming up, several types of windings are commonly referred as a package windings due to the arrangement of conductors into disc, and however the term most often refers to a coil type that is used almost exclusively in self-formed transformer, and the conductors are wound around a rectangular form with the widest face of the conductor oriented either horizontally or vertically, as you can see in the figure. So now this is a choice of the winding based on the voltage rating of the transformer as well as the kVA rating of the transformer, starting from a transformer for rural supply, distribution transformer, transformer secondary, uh, transmission transformer, primary transmission transformer. Obviously, these transformers are high voltage up to 440 volt. So these are different voltage and different kind of winding. Like first transformer for rural application needs typically normally is a rating of 1.6 to 100 kVA and high voltage typically of 3.2 or 11 up to 11 kV and low voltage is 0.440 volt or 0.44 volt and the typically winding for high voltage is coil and crossover or and low voltage is helical, and for distribution transformer with this or a small power transformer up to 100 to 1000 kVA is a high voltage maybe 11 to 33 kV. So use the foil and crossover disc multilayer helical and low voltage winding 0.44 kilovolt is used helical and multilayer helical. And transformers for secondary winding that is 10 MVA to 20 MVA and high voltage winding 33 to 66 kV of disc type and LV winding of 11 kV of disc type helical, and transformer for power transmission, primary transmission which is of 45 MVA to typically 150 MVA and high voltage side may be 132 to 440 kV use the disc or multi-layer helix winding, and low voltage side is typically maybe 11, 33 or 66 use this disc or helix winding. Transformer at generating station usually of 72 MVA to 350 MVA and high voltage winding is normally 132 to 275 volt, normal disc or multi-layer helix, and low voltage winding is typically your 11 kV or 22 kV with the disc or helix winding. So now coming to transformer thermal and mechanical performances. So as you can see about the thermal performances here with the mechanical. So convection, how it is the typically the heat through convection goes to from main body of the transformer to the you can say cooling tubes or cooling surface which are put in the transformer. How it is really heat is flowing from there and how it is, you can see how it is the winding as well as the core and how the radiator tube dissipate the heat which are concentrated losses in the winding as well as in the core. How it's really through the convection the heat is transmitted to outside environment like from the uh, generated from the winding and core. So there is IEEE guideline for the interpretation of type of cooling. We already discussed about the different kind of cooling like OAFA and non-detected FOA and FOW or detected, and then you have a typical class value for that. So now coming to here, the A4 level criterion has been developed to classify risk to transformer when there is no previous dissolved gas history for continuously operation at various combustion gas levels, and the criterion use both concentration for separate classes gases and the total concentration of all combustion gases, which called it TDCG, and for which the condition 1 is TDCG below this level indicate that the transformer is operating satisfactorily and any individual combustion gas consumptible gas exceeding specified level should prompt additional investigation. Now coming to the condition 2, TDCG within the range indicates greater than normal combustible gas level. Any individual combustible gas exceeding specified levels should prompt additional investigation. Action should be taken to establish a trend. Typically, the fault may be present. And condition 3, the TDSC with the range indicates a high level of decomposition, and any individual combustible gas exceeding specified levels should be prompt additional investigation, and an immediate action should be taken to establish a trend and fault are probably present there. So coming to the condition 4, TDSC with the ranges indicates excessive decomposition and continued operation could result in a failure of the transformer. So we should proceed immediately and with the caution, like. And this is the typically the table 1 for dissolved gas concentration, typically for different all these 4 conditions with different factors, like here of TD, even TDCG levels also, as we already talked about. So now coming to, again, typically about thermal and mechanical performance. So here we have a disk type of winding, as you can see, and direct with non-directed flow and directed flow, how the flow is there of cooling in all these, like all turns in a contact with the moving coil to lower hot spot temperature. And then you can just see, if we do the finite element analysis of the leakage flux between the coil, how it looks like, and flux leaks out the radially, whether there is an axial spreading out turns in a coil. So you can see the winding leakage flux plot, how it looks like. And then thermal FE plot, where you can see the red hot is the higher temperature and blue is with the lowest temperature. So how the temperature distribution in the transformer, typically in the core as well as in the winding. So now coming to the typically the insulation. So classes A, B, C, F and H are used in dry or non-oiled immerged transformer, and the silicone treated materials being advantageous because of their water repellent property. And for oil immerged transformer, the coil insulation is a class A material, generally paper or derivative thereof, and cotton is confined to small units. But the use of synthetic enameled or interturn insulation is increasing and may be extended to a low voltage winding up to 17.5 kilovolt of large unit. The cooling of the transformer differs from that of rotating machines in that no moving parts are available to assist the circulation of coolant. So if the natural thermal head resulting from the expansion and consequential upward flow of the heat coolant is not sufficient, the forced cooling is necessary. And you can just see how the typically the temperature distribution is there with the natural cooling in the different parts of the typically of the transformer with the oil cooling, like how the circulation and the temperature variation is there typically in the core, then duct and low voltage winding, then ducts, and then the high voltage winding, and then in the tube. And of course, what is it is all with respect to the ambient temperature. So you'll just find the highest temperature is virtually in high voltage winding, like where the conductor cross section area is certainly smaller, but the heat concentration is reasonably there. Like, so now you can just see how it is force acting on the HV and LV winding of a simplified rectangular 2 winding core transformed through the fault condition, as we call it, like how the typically the forces are produced and during short circuit, especially, or the any fault which may result closer to the short circuit, cause the a large electromagnetic forces between the conductors or in the windings. Like you can just see here the electromagnetic forces in the transformer under short circuit condition, how they are really defined in different parts of the winding of the transformer, and how it is going to be really affect the winding. You can say power class transformers are designed to withstand forces in all directions, because the short circuit current rating of the transformer is very high. Even we limit the short circuit current by enhancing the leakage reactance by changing the shape of the transformer windings and core, but still since the level of the current is very large, so it causes the large electromagnetic forces produced between the conductors. Like, so coming to typically this mechanical forces, the primary and secondary currents of the loaded transformer are in magnetic opposition with respect to the common core, but cumulative with respect to the space between them. So exciting leakage flux, and one important consequence is the production of mechanical forces of mutual repulsion. And the mechanical forces can be analyzed in the following component, like radial tending to burst outer and crush inner coils, and axial tending to compress coil lengthwise, and axial tending to force apart axially displaced coils. And you can see how the mechanical forces is there in the two type of conductors having different direction of current, how this is a typically kind of a forces are produced in between, and outer side goes outside, inner one it goes to the typically kind of attractive force. So how it is a repulsive and attractive force are produced in the different type of parts of the winding, and how it is, what it causes with the forces with the buckling of the winding of inner winding, and how it is typically outer winding goes like a hooping with the radial forces. So stresses due to radial forces, that hoop stresses in outer winding and buckling stresses in the inner winding. And now this is typically how it is a compression axial compression force at the center with this help typically of the sandwich winding. So stress reduced to axial forces cause compressive stress on key spacer and tilting of the conductors and axial bending between the key spacers. Like you can see how radial forces causing a buckling of the typically the inner coil, and how it is like a radial forces hoop stress on outer typically the coil. I mean the force as you can see here in the with the red color. The outer radial force converted to tensile stress. And similarly the axial forces, force obtained applying the left hand rule are produced how it is going to the typically the forces going to be actually in the coils. Like so coming to now vibration noise, the large power transformer for local distribution makes noise with major consequences, and under no load condition the hum developed by energized power transformer originate in the core, where the illuminations tend to vibrate by magnetic forces, and the noise is transmitted through the OL to the tank sides and thence to the surroundings. And the essential factors in the noise production are consequently magnetostriction, that is a extension of 0.00012 percent for a small flux density of 1 Tesla, and mechanical vibration developed by the laminations depending upon the tightness of clamping, size, gauge associated with the structural part, etc., and mechanical vibration of the tank walls and the damping. So now if a core consisted of homogeneous steel, the magnetostriction will cause vibration only in a plane parallel to that of the core, but as the laminations are not homogeneous, the differential movement take place within the core and exciting the vibration in a direction perpendicular to the plane of the core. So typically you can say how really it causes the conductor telescoping failure because of the short circuit duty, and typically a problem of layers winding can happen to disc or helical winding also. So extent of the damage to paper insulation will determine how soon a total unit failure will happen, and typically the how you can analyze the typically the fault failure like how, and then the fault failures, as you can see the how the winding is blown or burned, typically in different kind of the windings. Like now coming to typically the tangent behavior of the transformer. So apart from thermal tangent, short duration switching currents, line surge voltages may occur in the transformer operation of such magnitude as to impose high mechanical stresses or insulation damage. So first is the switching. When the primary winding of an unloaded transformer is switched on to a normal voltage supply, it acts as a non-linear inductor, and neglecting resistance, the applied voltage must be balanced at every instant by the EMF induced by the magnetizing current, and the behavior depends on magnitude, polarity and rate of change of the applied voltage at the instant of switching. And assume first that the core is initially unmagnetized and that is switched to close to a voltage peak, and the balancing induced EMF demands a flux having a maximum rate of change so that the flux start to grow from 0 in the required direction, and as also does the magnetizing current. So the normal no load operation is shown in figure A, where there is no tangent and you have a switching at the peak of voltage and flux start building up from 0. And however, the switch closes at voltage 0, as in case of B, the voltage is positive during first half period, throughout which the flux must therefore increase with the total change corresponding to that of normal of the half period. Now, if therefore reaches a maximum twice the peak, that is 2 phi m, a phenomena called doubling effect. In next half periods, the effect of losses rapidly reduces the flux waveform to symmetry about the time axis. So flux doubling implies a peak density of the twice the normal steady state value. So with the high saturation level, because of double flux employed for the modern transformer, the magnetizing current required for twice the normal flux is very high, and for a peak flux density of 1.4 Tesla, for example, the excitation is about 3 kiloampere turn per meter. For twice this flux density, it might increase to 100 volts, and the transformer switching tangent is referred to as the inrush current, and it causes difficulty in the application of current balance protection. And you can just see how it is like you do. I mean, this doubling effect can be more severe if there is already some remnant flux in the core, as it goes further. So it may go with again 2 phi m plus phi r also. So remnant flux in the core can aggregate this condition, and if the primary voltage applied at the 0 instant and in such direction that the rising of field augments the existing remnant flux phi r as in shown in figure here. The sinusoidal flux variation has still the magnitude of 2 phi m, but is entirely offset from the 0 and rises to a peak value of 2 phi m plus phi r. So this further increase the flux will cause further large inrush current during this period. So as you can see how really it goes to the magnetization characteristic of the typically of the core. Normally it is like a kind of BH curve, and down how it goes with the excessive saturation to go phi m, and further how it goes to phi m plus phi r, this flux, and what kind of magnetizing current it will need if you really compare from initial normal condition of this your BH curve too. So Husted loop in terms of flux and current are shown in figure D for cases A and B and C. The first loop is normal condition and is symmetrical. The second is unidirectional and loop area is actually reduced. And then the case C, so supersaturation almost negligible hysteresis loss. Now coming to peak magnetizing current approximately to that determined by the inductance of the primary winding, considered the air core coil because of the excess saturation, and the current peaks thereafter fall rapidly because of the rate of decay in the function of race of R upon L, where R is the large loss resistance, and as the flux density reduces towards the normal exertions, the loss resistance reduces but the inductance increases and slowing the rate of decay and causing the current distortion to persist for several seconds. And as you can see how it is a kind of normal magnetizing current to compare to that, how it is a inrush current waveform which really looks to be very manifold like. So the distorted current as shown in by the typical oscillogram, the condition typically of remnant flux can occur in 3-limb transformer also if one primary terminal is anized and later on then the other two if the neutral connection large inrush current characterized by an exponential decay, the DC component may occur. It virtually have a DC component here, and you can, if this phenomena can be typically analyzed as you say why the no load current is typically you can say and why inrush current is present there. So short circuit forces pulsates the twice the system frequency. So major and minor pulses gradually become equal to the offset current decaying and the fault current becomes symmetrical. So now coming to typically the surges. The surge over voltage initiated or overhead transmission line by switching faults or lighting discharges and may be imposed on the system transformer, and the surges may have a very steep waveform with the rate rise of 1000 times as great as the peak rate of the normal voltage at the operating frequency and imposing intense and rapidly changing electrical stresses within the transformer. And you can see how it is typically the because of the typically the coupling capacitances and with the surge voltage, how this voltage goes quite excessive across the distribution of the winding turns, which may be really causing the surge voltage distribution across the winding and may affect your winding even sometimes very excessive voltage may cause the typically the affect the insulation. You can call it the typically causing a crack in the insulation, which really with the second it goes with the time with the moisture and dust, it really affect the insulation life. Now coming to the objective questions. So first question is the which type of cylindrical winding use circular conductors employed in this in multi-layer type of cylindrical winding, and helical windings are used in power transformer and disc windings are used in the high capacity transformer, and helical windings with rectangular strip conductor is generally used for LV coil, and the reason for single phase cell type distribution transformer to have sandwich type winding is used in typically to save the copper as well as to improve the voltage regulation to reduce the typically the leakage reactance. So if the frequency of the supply voltage to the primary of the two transformer is double, then the induced EMF will be double. And in the transformer, the induced EMF per turn is determined in terms of the kV output. So it equal to K under root Q. In case of the design of transformer, the usual value of the ratio of the window height to window width is order of 3. The large value of current density can be adopted for transformer applying cooling, that is used for oil force water cool, and large value of flux density can be adopted while designing the large capacity power transformer. And the overload capacity of the transformer depends on core size, and the crossover coils in transformer are generally used for high voltage winding. And if the single phase transformer of 6.6 kV about 400 core type, the induced EMF per turn 6 volt, then the number of turns in HP winding, you can just calculate in the method given here, it comes 1122. If the gross area of window is 750 centimeter square for a particular transformer, then the approximately height of the window is your from calculation you can calculate this comes 50 centimeter approximately. The percentage of silicon in the transformer core steel is normally 4 to 5%. And what are the effect of marking limb section lower than the yoke section? Typically, it causes all economy of copper, decrease in iron loss as well as decrease in magnetizing current. And the core laminations are prepared using cold rolled granted steel for large capacity transformer, and circular coils are prepared in transformer of typically of superior mechanical stability for subsequent, and it becomes waste to apply the coil. Then now the magnetic strength cause the humming the transformer, and humming noise in transformer can be decreased by different method by using low flux density, tightening the clamping of laminates as well as suitable cushion padding and oil behavior. Now coming to solved numerical problem. So we start with the first numerical problem. Determine the dimension of core and window for a 125 kV 50 single phase oil emerge core type transformer. Assume flux density as 1.23 Tesla, current density of 2.5 ampere per millimeter square, and window space factor of 0.32. Take EMF per turn of as 17 volt and design the cruciform core with the window height as 3 times the wind. The flux density is given here 1.23 Tesla, and current density is given delta 2.5 ampere per millimeter square, and height of the window is 3 times width of the window, and window space factor 0.32, EMF per turn 17, and kVA rating is given 1 turn. Now coming to volt per turn, ET equal to, and you can find out that's a 4.4 F phi m. So you can find out phi m equal to ET 4.4. So it comes 0.0765 Weber, and net iron area is phi m upon bm. That comes putting value 0.062 meter square. And for cruciform net area is AI equal to 0.563 square. So from this you can find out D, putting value of AI divided by under root 5.6, it comes 0.332 meter. Now width of the largest stamping, now A equal to 0.85 D, where the A you can calculate 0.282 meter from this, and depth of the yoke is width of the stamping. So width of the smallest stamping B equal to 0.53 D, that comes to be putting value in this formula is 0.175 meter. And height of the yoke, that is hy equal to 1 to 1.5 A. So at y putting value this, it comes 0.282 meter. And kV rating of single phase transformer, your Q equal to 2.4 for F delta AIBM AW KW 10 power minus 3. The putting the value of this AW comes 0.0184 meter square. And now if you can say HW equal to 3 HW, so AW equal to HW, so AW is 3 W square, and that is 0.0184. So WW under root, you can put the value and get the 0.078, and HW equal to 3 HW, that comes 0.234 meter. And overall depth of the transformer A equal to 0.282 meter, and overall height H equal to W plus 2 HY 0.79 meter, and overall width of the transformer W equal to W plus D plus A, that becomes 0.688 meter. Now you can see all the dimensions here of cruciform with the cruciform core, which are we calculate. Like coming to numerical problem 2, a 3-phase 50 Hz oil cooled core type of transformer with 2-stepped core has the following dimensions. So distance between the core centers is equal to 0.21 meter, height of the window 0.34 meter, diameter of subcoming circle 0.145 meter, flux density in the core is 1.15 Weber per meter, current density in the conductor 2.8 ampere per meter, and estimate the net iron and window width. So AI equal to 0.56 D square. So putting value of the D here, it comes 0.01174 meter square. So for 3-phase core type of transformer, D equal to small d plus WW. So WW will be D minus small d. So it comes 0.065 meter. And area of the window AW equal to AW into WW. Putting value, it comes 0.0221 meter square. Now coming to numerical problem 3, for a 350 kVA 3-phase 50 Hz star delta 11 kV to 3.3 kV core type of distribution transformer. Assume the distance between the core centers as twice the width of the core. Calculate the diameter of the 3-step core, depth of the yoke, and width of the height. So solution is Q equal to 350 kV. Transformer rating 3-phase star delta. So what is rating 11 kV to 3.3 kV? So for 3-phase core type of transformer, it equal to 0.45 under kVA per phase. That comes 4.86 volt, and 6K is 0.45 for 3-phase core distribution transformer, and 5 equal to ET upon 4.4 F. So it comes 0.0219 Weber, and AI comes 5M upon BM. So it comes like putting value 0.018245 meter square. So for 3-step core, AI equal to 0.6 D square. So putting the value, it comes 0.018245 meter square, and D from this you can calculate from the relation. So after putting value, it comes 0.1732 meter. Now the width of largest stamping, that is equal to 0.9 d, that comes 0.1558 meter, and depth of the yoke dy equal to a, it's a 0.1558 meter. We know that q equal to 3.33 f sigma ai bm aw kw 10 to the power minus 3. So from this putting a value, we can find out kw equal to 10 upon 30 plus kV, so it comes to 0.24, and from this equation, output equation, we putting the value, we will get aw equal to 0.16 meter square, and given that the distance between the core limbs is d equal to 2a and w equal to w plus 2d equal to a, so w is equal to 0.1389, as w will be aw upon ww, so it comes 1.156 typically the meter. Now coming to numerical problem 4, a 3-phase 50 Hz oil core transformer has the following dimensions. The distance between the core center is 0.2 meter, height of the window 0.24 meter, and diameter of subscribing circle 0.14 meter. The flux density in the core 1.25 Weber per meter square, current density in the conductor 2.5 ampere per millimeter square. Assume the window space factor of 0.2 and core area factor of 0.56. The core is two-stepped. Estimate the kV rating of the transformer. Here all the parameters given: frequency 50 Hz, Bm equal 1.25 Tesla, d equal to 0.2 meter, and sigma equal to 2.5 ampere per meter square, Hw equal to 0.24 meter, Kw 0.2, d equal to 0.14, and Ai 0.5 d square. So we can say Q equal to 3.33 F sigma Ai Bm Aw Kw 10 to the power 3, where Ai is 0.56 d square, so it comes 0.0109 meter square, and for 3-phase cotan d equal to d plus ww, small d plus ww, so ww is d minus d, that comes 0.06 meter, and aw equal to aw into ww, that comes 0.0144 meter square. Now q, putting the value all these parameters in this relation of q, it comes q equal to 16.33 kVA. Now coming to numerical problem 5, calculate the core and window area of 125 kVA 2000 by 400 volt 50 Hz single phase cell type of transformer. Flux density is 1.1 Tesla, current density 2.2 ampere per meter square, volt per turn is 11.2 meter, and window space factor is 0.33. Assume a rectangular core with a stamping of 7 centimeter width. So Q equal to 1.125 kVA. So volt and type of transformer is that 2 kV upon 400 volt single phase cell type. So Bm is 1.1 Tesla, sigma is 2.22 meter ampere per meter square. So volt per turn is 11.2, Kw is 0.33, and window stamping is of A equal to 7 centimeter. So volt per turn is given by Et equal to 4.4 phi m, that is 11.2. So phi m comes, putting the value 0.05 Weber, and Ai now Bm upon phi m upon Bm, that comes 0.045 meter square. Now typically the kV rating of the cell type transformer is given from the formula, so it comes, and putting the value of this rating 125 kV and other parameters, Aw comes 0.03 meter square. Now coming to numerical problem 6, it is 125 kV, 2 kV 400 volt 50 Hz single phase cell type transformer, assuming a rectangular core, stamping of 7 width, and the ratio of height to width is 3, window area is 0.03 meter, and the core area is 0.045 meter square. Calculate the height, width of the window, and overall height and width. So the central limb carries windings, and so the flux in the central limb is twice that of the outer limb, and hence the area of the cross section of central limb is twice of that of the other limb. So coming to here, to get all dimensions, the gross core section of the central limb is 2a into b as shown in the diagram. The overall width is capital W equal to 2 WW plus 4a, and overall height is equal to HW plus 2HY. So given a stamping of 7 centimeter, width, so height is equal to 7 centimeter and 2 equal to 14 centimeter. So area of the window, W is given 0.03 meter square, so W upon WW is 3. So AW is 0.03, that is 3 times W square, so WW is 0.1 meter, and HW equal to 3 into 0.1, that's 0.3 meter. And the gross section area of center is 2a into b, so overall width is W equal to 2 WW plus 4a, that comes 228.2 meter, and overall height H equal to HW plus 2HY, it comes 0.44 meter. Coming to numerical problem 7, determine the main dimension of the core and window for 1250 kVA, 33 by 6.6 kV, 50 Hz 3-phase core type of power transformer based on the following information of design parameter. Maximum flux density in core is 1.5 Tesla, average current density is 2.5 ampere per millimeter square, window space factor of 0.21, net area of 3-step core AI equal to 0.6 d square, and window positions 3 into 1, and full load magnetic loading MF ratio is 1.6687 10 to the power minus 6. So coming to now mid dimension of the core, so full load magnetic loading of 2 MF is 1.687 10 to the power minus 3. So that's R is equal to 5 upon Ni or MF, that is 1.687 10 to the power minus 3. So K factor is that is under root 4.4 FR 10 power 3, so it comes 0.612. And for 3-phase transformer, EMF per turn can be calculated K under root Q per phase, that comes to 12. Putting a value 12.5 meter, and the net per turn, and the net area Rn area is A equal to ET upon 441 F5 PM, that comes 0.0375 meter. And for 3-step core, A equal to 0.6 d square, and the diameter of the prime circle now d will be under root at A upon 0.6, that comes 0.25 meter. And main dimension of window, that is average current density sigma 2.5 ampere millimeter square. So total output of the transformer with the output equation Q equal to 3.33 F BM delta kW AI AW 10 power minus 3 kVA. So putting the value in this, so AW comes your typically 0.254 meter square. So now the area of the typically window is AW equal to L in bracket D minus capital D minus small d, and given that window proportion L upon D minus D3. So solving these two equations, so we get a height of the window L equal to 0.87 meter, and width of the window D minus D 0.29 meter, and central to central distance between the core D equal to 0.54 meter. Now coming to numerical problem 8, calculate the net cross section of core, cross section of core dimensions, window area, dimensions of window for a 200 kVA, 6.6 kV, 250 volt, 50 hertz, single phase, cell type of all merged self-cooled distribution transformer based on the following parameters: window space factor Kw equal to 0.28, window maximum flux density in core Bm equal to 1.1 Tesla, average current density sigma equal to 2.2 ampere per meter square, window proportional HW to WW 2.5 to 1, and rectangular core portion length of core to width of the core is 1.8 to 1, and net cross section area of copper in window is 0.2 times the net cross section area in the iron of the core. Now coming to the solution, net cross section of the core will be according to the given condition Kw into AW equal to 0.2 AI, and output of this single phase cell transformer Q equal to 2.22 F BM delta 6 Kw AW AI 10 power minus 3 kVA. So putting the value here, you can get the value of AI equal to 0.061 meter square, and gross area of the core, the stacking factor of the core is considered 0.9. So thus gross area of the core is typically 0.061 divided by 0.9, that is 0.678 meter, and core dimensions here proportional to rectangular core is 1.8 to 1. So thus the length of the core to width ratio is 1.8, and moreover 0.078 equal to length in the core and width of the core. So length of the core is 0.35 meter and width of the core is 0.19 meter. Now coming to the window area can be find out from equation of the window HW KW. So that's KW AW 0.2 AI. So from this we can find out value of AW equal to 0.0436 meter square, and dimension of the window, now we can find out window proportional 2.5 to 1. So now the height of the window is typically height to width window is 2.5. So AW is 2.5. AW into WW is AW, that's a 0.0436. So solving these two equations, we get height of the window 0.33 meter and width of the window is WW 0.13 meter. Now coming to numerical problem 9, the window in the magnetic frame of 50 kVA, 3.3 kV, 254 volt, 50 hertz single phase core type distribution transformer, gross area available area of 0.034 meter square. The value of various design parameters are as follows: window space factor Kw equal to 0.26, maximum flux density in the core Bm equal to 1.2 Tesla, average current density equal to 2.1 ampere per millimeter square, sectional area of the core for square section AI equal to 0.45 d square, and width of the core for square section BC equal to 0.71 d. And based on the above information, estimate the following: section area of the iron in the limb and diameter of the circle round the square cross section area, dimension of the window if the distance between the centers of square is twice of the width of the. So now coming to solution, section core area is the core cross section area of the core can be found out from the output equation, that is Q equal to 2.22 F BM sigma Kw AW AI in 10 power minus 3 kVA. So you get from this AI equal to putting value 0.0202 milliliter square and diameter of the circle A equal to 0.45 d square. So from there you get d equal to 0.21 meter, and dimension of the window width of the core of a square section BC equal to 0.71 d, that is 0.15 d, and distance between the centers of a square section d equal to b. So d equal to, putting a value of 2 into 0.15, that's 0.3 meter, and width of the window is, that's d, capital D minus small d, 0.3 into small 0.15, that's 0.15 meter, and height of the window L equal to AW upon WW, that's a 0.227 meter. Now there are, based on that, there are some unsolved problem which you can solve with the answers argument. You can verify the answers with by solving this, and for this purpose we have followed the following references. You need, you can go through these references and look into additional material, and thank you very much.